So what it means, if the exponent is n, that means if you take every element in the group and put it with itself n times, if you combine it with itself n times, you will get the identity, no matter what the element is. So let me, and I'll explain why Cn has exponent n in just a moment. So number one, so here are the problems for next week, and I hope it'll get you juiced up kind of for the group theory part of the next test and stuff I asked you on that. And by the way, I've asked for long 216 at 7 o'clock next Wednesday, and I'll let you know when I hear something. Show if G circle and H star are groups, then the direct product, that is the set of all ordered pairs, first coordinate from G, second from H, is a group. If I define the operation B, how do I combine these two things? I use circle in the first coordinate and star in the second coordinate. Just show that that's a group using the fact that both G and H are groups. That was one of the things I promised you last time. Number two, this problem's a classic and it's fun. Show that every group with exponent 2. Okay, what it means for a group to, what it means for an element to have order 2 is means when you combine it with itself, G squared, it's the way I wrote that, then you get the identity. To be exponent 2, every element in the group has that order, right? So in other words, you've got this big group that has every element, when you square it, it's the identity. By the way, don't make the mistake of assuming that this can be a small group. In fact, these groups can be arbitrarily large, even infinite. You can have infinitely many elements in the group, all that have order 2. Any group with exponent 2, automatically abelian. That is A times B times A for any pair of elements in there. This is not true for any number bigger than 2, but for 2, it's magic. Yes?
So when we say squared, is that in relation to whatever relationship?
That is exactly right. So if the operation is circle, when I say G squared, I mean G circle G, right?
And if it's addition, then it would just be
G plus G. Okay. Exactly. That's exactly right.
But only, I guess, really only one operation, 2 numbers.
That's exactly right. And one of the conventions in group theory that isn't universal is oftentimes if you have an abelian group, the operation is written as addition. But I will usually write multiplication, whether it's abelian or not, except in some certain cases like Z mod n. Number 3, find all subgroups of the integers under addition and show that your list is complete. Actually, I told you yesterday what the list is. Show that this is a complete list. And I will give you a hint on this. Some of the properties of integers will be very important in classifying these groups. That is the Euclidean property. The Euclidean algorithm might be useful or one of its consequences. Okay, those are sort of the problems that I promised you. Here is something that I'm going to talk about this later, but you can use this freely. We're going to consider the subgroup S7 for problem 4, but here's some general facts about any SN. If we have C is one of these cycles that we talked about, then we say C is an M cycle if it's got n things in it, right? So for example, something like this. Well, actually, since I do have some answers, so I'll do that in a moment. I'll sort of add to this in a moment. So an M cycle is something with n numbers in it that are all different. The order of any M cycle. You might do this just to amuse yourself, although I say that you can use this freely. The order of any M cycle is M. So if you have a 5 cycle, you have to do it to itself 5 times before you get back the identity and so forth. Any element in Sn can be written uniquely as a product of disjoint cycles, right? And that actually follows from stuff that we talked about last time. And finally, and this is interesting, if you have an element of Sn, you can write it as disjoint cycles. What's the order of this element? Well, look at all these disjoint cycles and see what their length is, their order is, and take the least common multiple of the order, right? So in other words, if you have a 5 cycle times a 3 cycle times a 2 cycle, and they're all disjoint, then the order of that thing is going to be the least common multiple of 5, 3, and 2, which I guess in this case is 30. So here is your task. Consider the group S7. Make a list of all types of elements that are possible. Don't list, my God, do not list all the elements. There's 5,040 of them. But list all the types, like by their cycle type. For example, one type might be A, B, C, D, E, F, G, right? You might use all 7 of them. Another type of element you might see is you might use 4 elements and then 2 others, A, B, C, D, and then E, F. List all possible cycle types that you might get. The list is not very long, right? For each cycle type that you find in part A, find its order using that up there. That'll be kind of interesting. And then this is just like going back to the old poker problems. How many elements of each cycle type are there? So for example, we're in S7. If you use all 7 numbers, A, B, C, D, E, F, G, and make a 7 cycle, how many of those are 7 cycles? Your last problem is checkable because if you get it right and you add up all the cycle types, you should come up to the order of S7, which is 5,040. So you can check yourself on the last one for sure. Okay. Let me go. Get this organized here. Okay, so let me say a couple things. Now, 1, 3, 2, 4, 6. And, you might have this element here. This is a 5 cycle times a 2 cycle. They're disjoint, right? So the order of this thing is the least common multiple of the orders. The order of this is 5. Least common multiple of 5 and 2 is 10. This will have order 10. How many things in S7 have a 5 cycle times a 2 cycle? Make the list of all the cycle types and count them up. Make sure that you record their orders and see if you get it. So that should be kind of a fun problem. Okay, so this is the question you were asking about. Why is the exponent? So let me point out. Let me do a specific example, then I'll go to the general. Everybody agree with that? And our addition is sort of like a clock. Right, it's sort of like the clock modulo 6, right? So what are the orders of the elements here? So let's see if we can figure that out. What's the order of 0? How many times you got to add 0 to itself to get 0? Once. What's the order of 1? How many times you got to add 1 to itself to get 0?
Oh, but this is.
But in Z6 you can't. Oh, you're close. Yeah, that's right. 1, 2, 3, 4, 5, 6 bars. So that's the first time you come to 6. So this has an order. What's the order of 2 bars? 2, 4, 6. Agree? So must be order 3. Everybody catching on with this? So we have a list of elements. In order, we have those the orders of these elements in order are 1, 6, 3, 2, 3, 6. the exponent of this group what's the smallest power that if you take every element in that group to that power, or in power, I mean by adding to itself an appropriate number of times, what's the smallest element or the smallest positive integer that you can add anything in here to itself and it gets you to the identity? Well, it's got to be at least 6 because it takes 6 for 1. Agreed? Got to be at least 6. And notice since these other numbers divide 6, it's going to work for them. Because if I take 2 and add it to itself 6 times, I get multiple 6, and so forth and so on. Everybody agree? So more generally, now it's harder to make a list here because of the fact that I don't know what n is, right? N might be a prime or n might have a whole bunch of factors. I don't know, but I do know this. This still has order 1 and this has order n. Everybody agree with that? So the exponent of Zn must be at least n. Agree? But notice, if K bar is in n, then n times K bar, which is K bar plus K bar plus K bar, n times is 0 bar. Right? Because basically, since I'm adding K bar to itself n times, I'm going to get a factor of n in there, which makes it 0 in Zn. So what do we got? Well, I know that the exponent has to be at least n because it takes n for this. And now I know that the exponent because now I know that n works for everything in there, right? So the exponent is exactly.
So will all of the other orders of the other elements be factors of n?
Yes, actually, it turns out, and that's a general theorem that we're going to get to. It turns out if I give you any finite group, right, any finite group, then order of any element divides the order of the group. So that's good move. It was a spoiler, but you know, you got us there. The order of any element divides the group. So as an example, to sort of bolster up that, arrangements. It turns out, and actually we're going to discuss this later, the number of arrangements on Rubik's group is this large number. This is about 43 quintillion, right? This is the number of rearrangements that I have on Rubik's Cube without cheating pulling apart. Now, let me give you some examples. Let's call this element X. See what I did? I turned it 180 degrees. That has order 2, because when I do that twice. Let's call this element Y, where I just turned it 90 degrees. 1, 2, 3, 4. That had order 4, right? But this will, how about this? Do it twice, 3 times, 4 times, 5 times, 6 times. That had order 6. Everybody okay so far? Notice all those numbers, 2, 4, 6, they all divide this number. Agree? The one I did, and I'm not going to go through it again, the one I did like this and repeated over and over, that had order 105. Right? Notice 105, let's see, how can I get 105? 105 is 3 times 5 times 7. So there's a 7 there, there's a 3 there, and there's a 5 there. Right? So yes, it divides. What is the smallest number, given what we've discussed so far, what's the smallest number where there's no rearrangement on the cube that takes exactly that many times to come back to the identity? But the smallest number you know for sure can't happen.
Just the n.
What's that?
Just the n.
What's it?
The size.
Actually, you were correct in the sense that there is no element that has that order, right? Very big. But smaller. Do you think one's smaller? Yeah.
Could be 13.
13. Notice that every prime, 2, 3, 5, 7, 11, all divide this number. 13 is a prime. There's no way 13 divides this, right? And in fact, it turns out that any number up to 13, I can find you something on the cube that takes exactly that many times. But yes, 13 is the smallest number that there's no arrangement that has order 13 in the cube. Okay, so any questions on that? Last time, I defined something called a homomorphism. Homo meaning same, morph meaning change, same change. And here's the idea behind a homomorphism. I'm going to define it for you again. Definition. G circle star groups. A homomorphism we'll call it phi, is a function phi of G1, G2 is phi of G1 star. Let me kind of explain this a little bit. Notice here what's going on. The action's going on in G. So you combine these two elements of G under the circle operation. That should be the same thing as phi of G. Remember, this is an element of H. Phi of G2 is an element of H, and you combine them on the star. So basically, this function preserves, it respects the group structure. All right? And I'm going to add one more little thing to the proceedings here, and then I'll give you kind of a couple of examples. If there's also one and onto so if this function is also bijective, so it pairs off the elements, there's a one-to-one and onto function here, and this is also called an isomorphism. So that's a homomorphism that's also one-to-one. Let me tell you what this is all about. Let me give you a couple of groups here. Why do we care about this? Well, there's an old familiar friend. And here's another group. I'm going to just call this one G. And this one is under multiplication. So let me tell you what I mean. So basically you multiply by adding exponents, right? So for example, 1 times any of these other things leaves it alone, right? Everybody identify 1 as the identity. 1 times any power of that is just 1. Right? What do you suppose a times a squared is? A cubed. That's what I was supposed to. Okay, but here's my caveat. What do you suppose a cubed times a to the 4th is? Correct. A cubed times a to the 4th is a to the 7, which I don't know much. This is a to the 6 plus 1, which is a to the 6 times a, which is a. Because remember, a to the 6th is 1. So this kind of cycles back. It's very much like the clock. It goes 1, a squared, a cubed, a4, a5, a6, back to 1. And then it goes through the cycle again. Now, these two groups are different. Promise, right? This one, you combine things under addition. This thing, you combine under multiplication. Everybody agree with that? But would everybody agree that these two groups are essentially doing the same thing, right? They're doing a clock thing, right? It's the same thing here. Here is an isomorphism between these groups. Everything basically corresponds to its exponent. Everybody okay with me? The whole idea behind isomorphism is this. These groups are not the same, but they're spiritually the same, right? Because they're isomorphic. Two groups that are isomorphic are essentially kind of the same thing. Maybe they're disguised a little bit under different nomenclature. In fact, this one's addition, this one's under multiplication, but the spirit of the group is the same. Notice what this phi, it preserves the structure, right? If you look at phi of 1, so for example, 1 bar plus 4 bar. What is this? Well, this is phi of 5 bar, because after all, that's what 1 bar plus 4 bar is. And phi of 5 bar is a to the 5th, right? Everybody agree? And I don't know much, but I know a to the 5th is a times a to the 4th. And this is phi of 1 bar times phi of 4 bar. So see how we do the homomorphism, right? It has this, here the circle is plus and the star is multiplication. And so it preserves the spirit of this. Let me give you a little theorem about homomorphisms. That'll give something fun for after this. Here's something that's really cool about homomorphisms. And actually, I've got this as a later example, so I got kind of excited here. So let me justify this one a little bit. So what this says is homomorphisms have one neat property. Whatever the identity is over here, the homomorphism has to take the identity. That's what the first part says. Everybody okay? Why is this true? Now, you're going to think that this is just horribly cheating. I don't know much about the phi of the identity of G, but I do know it lands somewhere over here in H, so I'll just call that H, just for chuckles. Everybody agree with it? Now notice, here I'm writing both operation and G and H is the same thing, right? I'm not going to make a distinction in this exercise. Everybody okay? Anybody see how I can rewrite this? I can write phi of the identity of G times phi of the identity of G as phi of the identity of G times the identity of G. There's the homomorphism part. And what is the identity of G times the identity of G? It's the identity, right? The identity of G. So let's see what we've got. We've got phi of the identity of G is H, but it's also equal to H squared. Agree? So I don't know much, but I know that H squared equals H. And let's just multiply. Let me spread this out for dramatic intent. Let's just multiply on the left by H inverse. And what do we get here? This becomes H to the first power, and this is H to the 0 power, which is the identity of H. And so, phi of the identity of G . Any questions on that? I'll leave this for an exercise. Let me give you another example that you may have seen before.
Wait, really quickly, what is the, in this case, the inverse of H? Is that just like 1 over H, or is that like another element?
H is an element of a group. Yeah, so it's just some other element. Remember, in the group H, in fact, in any group, if you give me any element, in this case, I'm worried about H, then H has an inverse in the group.
And what does that inverse do again?
H times H inverse takes you back to the identity.
Okay.
Right.
Thank you.
I'm going to give you two groups here. So here's another example. Two groups. My first group is going to be the positive reals under the operation of multiplication. Okay, so imagine taking everything on the real line to the right of 0. What happens if I multiply two positive real numbers together? What do I get? Another positive real number, right? So it's close. Multiplication of real numbers is associative, right? So we got that. What's the element that leaves, that I can multiply any positive real number and it leaves alone? 1. And 1 is also a positive real number. So we've got the identity. Given any positive real number, call it alpha. What's its inverse? 1 over alpha, which is still positive and real. Everybody agree with that? So this is a group. Positive real numbers under addition. Here's my second group. I'm sorry, positive reals under multiplication. My next one's going to be all the reals under addition. Different operation, and now I've got positives and negatives, right? In calculus, you saw a group isomorphism from G to H. Anybody know what it is? If anybody guesses the right answer, I will log it on my spreadsheet. How about this? Let's see. Plus under multiplication. This is actually a homomorphism. Here's the reason. Suppose that X and Y are in R plus, so these are positive real numbers. This is the log of X times Y. And what is true about the log of X times Y that's been beat in your head ever since you were in high school? What's the nice property of logs we have here? That's right. Turns multiplication into addition. This is f of x, which is exactly what that homomorphism is supposed to do. Okay. Notice F is an isomorphism as well. And let me go through that verbally. What do I need for F to be an isomorphism? Well, think about the graph of the natural log of X, right? Notice that the natural log is always an increasing function. In fact, you can take its derivative, it's 1 over x, which is always positive. So it's an increasing function. Therefore, it must be 1 to 1. Everybody okay with that? And what is the range of the log? The range, the y coordinates are all of them. So it's on 2 as well. Everybody okay with that?
I have a quick question.
Mm-hmm.
On the left, we say f of x times y is the natural log of x times y. And then we have natural log of x plus natural log of x.
Oh, I'm sorry. I didn't even see
Okay,
that.
I wasn't sure.
That's a y, yes.
Okay.
Here's another thing. Let me record this just for fun. G, the positive reals under multiplication. What was the identity of this multiplication? Right. What's the identity here? Reals under addition.
0.
Now look at this theorem. This theorem implies that the natural log of 1 must be zero. because of the fact that the log is a homomorphism, the natural log of 1 has to be 0. Right? So there's kind of an algebra kind of thing that you can apply to this right here. By the way, there is a homomorphism there's actually an isomorphism that goes in the other direction. Anybody want to guess what this is? This time a homomorphism from all the real numbers under addition to positive reals under multiplication. And you can see if you can verify that this is a homomorphism in the other direction. It turns addition into multiplication, right? And again, it's a homomorphism in the other direction. That means that e to the 0 must be 1. Okay. Any questions? Questions? So we're going to talk a little bit about homomorphisms later, but homomorphisms are a way to map a function between two groups that preserves the structure. And we especially like isomorphisms because that gives a one-to-one correspondence, like in this example. In the next section here, we're going to start counting. So I'm going to focus mostly on finite groups here. So I'm going to call this counting in Lagrange's theorem. So let me just go ahead and give a spoiler. I'm not going to build it. I'll just tell you what Lagrange's theorem is. And I'm going to put in an undefined term here that I will define at the moment. The group with one. So here I'm assuming that G is a finite group, because otherwise you will see in a moment the theorem doesn't make much sense. If A is a subgroup of G, then the order of H divides the order of G, and if X is in G, then the order of X divides and actually I'm going to have one more statement to this, and that is the quotient I mean, after all, we've said that the order of H divides the order of G, so that quotient's an integer. The number of left cosets. You should not understand that statement yet. I haven't told you what a left coset is, but be patient, our Power 1 learners, and we will get to that soon. Okay. So I think the first part's understandable though. So if I have a group of order 100, right? If any subgroup of that group of order 100 has a number of elements that divides 100. So, for example, if I've got a group of order 100, can I have a subgroup of order 50? You bet. By the way, if I've got a group under order 100, I know of two subgroups for sure. One's of order 100 and one's of order 1, right? The whole thing is just the identity. 50 is on the table, right? 25 is on the table. 10 is on the table. 30 is not on the table. It is impossible for there to be a subgroup of 100 or 30, right? Let me point out that for some groups this is true, but for some not. So it is not true. Yes, the order of G n and divide n, then G has a subgroup order. This is not generally true, right? So, for example, I'll give you a concrete example. By the way, anybody remember what this is? 5 factorial, which is 120. Notice 30 and 40 both divide 120, but it turns out this particular example is like these subgroups. So the first thing I'm going to do is clear up what I mean by this so-called left coset. I'll do some examples of this too. So what do I mean by a left coset? Definition. But G being group and H and G a subgroup. A left coset of H and G is a set of form an element x little h, this left coset is called a representative. So let me give you an example. A couple of examples. Let G equal C equal 5Z. Now these are infinite groups, but the definition of coset is the same all over. Okay. Give me an integer, any of them.
7.
7, okay. So I want to know okay, notice instead of multiplying by the group that I use that notation, I'm adding because C has an additive structure, right? What is this? Well, this is just, I mean, think of it this way. This is 7 plus 5Z minus 10 minus 5, 0, 5, 10, 15, etc. So this coset is basically 7 plus everything in there. So it's just this big set of numbers. Minus 3, 2, 7, 12, 17. Extending in both directions. Let me pick another number. Let me pick 1. What's the coset 1 plus 5Z? Minus 9, minus 4, 1, 6, 11, 16, 21, 7. Everybody agree with that? Notice there's nothing in common between these sets because 1 plus 5Z, that's the same thing. All these numbers, what do these numbers have in common? These are all the numbers that when you divide them by 5, you get a remainder of 1. Everybody agree with that? What do these have in common? These have the property that when you divide them by 5, you get a remainder of 2. And notice you picked 7, but 2 and 7 are the same mod 5. Agreed? Notice that this coset is the same thing. I'll give you the same set of things. Let me give you a fine example. And this is why we use the word left. Left of coset doesn't matter because the operation is abelian. Elements 3. Let me pick a subgroup. Okay, well, your turn. Pick me any element of S3, anyone. Okay, so let's do this. I'm going to make this coset here. Roll of X being played by 1, 2, and roll of X being played by 8. What is this? Well, this is 1, 2, and then 1, 2, 1, 2. This is, if I multiply this out, 1, 2, and 8, which is the same thing as H in the first place. Connor, pick me something else.
What did you do?
I just multiplied everything in H on the left by 1, 2. I'm going to do the same thing. 1, 3, 2.
Know that 1, 2 times 1, 2 is the
Right. Just do the multiplication. Where does 1 go? It goes to 2 and then back to 1.
Oh, I see.
2 goes to 1, back to this.
Okay.
This is 1, 3, 2, E, 1, 3, 2. And so for this one, I'm going to have to do some multiplying out. This is 1, 3, 2. And this, let's see, 1 goes to 2, back to 1, so 1 was left alone. 2 goes to 3, and 3 goes to 2. Let me pick another one. How about 2, 3? 2, 3, E, and 2, 3, 1, 2. So this is 2, 3, and this is 1, 3, 2. I'll multiply this out. And let's look at one more. I've never seen a 1, 3. One, 3, E, and 1, 3. So I get 1, 3, and 1, 2, 3. Notice, I want you to notice a couple things about cosets, and we're going to show this next time. Number one, notice the cosets are all of the same size. Everybody agree with that? 2 elements started here. Every coset that I had 2 elements in it. Everybody agree? And there's something else that we're going to prove, and that is given any 2 cosets, they're either exactly the same, like these. I got the elements out of order, but it's the same set, or they've got nothing in common. That's 2 big things we'll learn about cosets, left cosets. They all have the same size. And number 2, they either are exactly alike or there's no overlap. Okay, we will pick it up there on Monday. Any questions? Okay, don't forget you've got homework due at noon. And other than that, y'all have a good weekend, and we'll see you on Monday. Yes, absolutely.